Okay, so here's our second topic. We're now going to discuss those measurements that we took, which is what differentiates math from physics a lot, right? We have to actually go out and get our own measurements. We now want to put those in equations, okay? And it's very, very math-based today. We need to work on some algebra skills. Before we get to the math part, though, we want to talk about some categories of measurements you'd take. You probably know these because they're part of grade 10 curriculum. It's scalar and vector. Okay? When you measure values, there are some values that logically you can only just give me a value for, like how heavy something is or how long something takes. But there are some values that I can give you a direction to. Like, as an example, I could tell you that you went 100 kilometers east. I can't tell you a direction for which way my mass exists, or like how long something takes. Is it north, south, east, or west, right? But there are some things in which directionality makes a difference. So we have a way of notating that. We call them scalar and vector. Scalar, all you care about is the direction. Sorry. All you care about is the magnitude. In vectors, you care about how much it is, but you throw a direction on it. And it matters. Right? A silly example I gave my grade 10s last year when I was teaching them this for the first time was, imagine there was a new student in the building, and they were lost, and they were right outside my classroom, and they wanted to find the office. And you said, oh, the office is easy to find. It's about 50 meters away. That was useless, because 50 meters means they could go, well, probably not up, right? But they could go any way you want, right? Good luck. Dig down 50 meters, you'll find it, right? But that's why you'd want to be more specific and say, well, it's 50 meters that way down the stair, right? Like you get the idea that directionality sometimes matters, and sometimes it doesn't matter at all. Right? So that's the vocabulary we use: scalar versus vector. And one of the most common initial terms we use to teach this is distance and displacement. As a really silly example, I'm going to walk around the desk here. Ready? 1, 2, 3, 4, 5, 6, 7, 8. I just call that 8. Okay. Well, that was the distance I traveled. I traveled 8 meters. Displacement, though. Yeah. Started where I finished. The way probably displacement was technically. Now, it's really all about straight line distance. Start. We often use this symbology to help represent in red, which is like a little accent or little arrow. You guys familiar with that? It notes vector. That's all. You see that little note on top of it? It means you care about direction. What I want to show you this one right here. This triangle. If you don't know this, it's the Greek letter delta, and delta stands for change. So if you're looking for how things change from one spot to another, so if you want to know your displacement, you know your final reference place, your initial starting place. Example. Asking, because someone might say 2, someone might say 8. Right? If I ask you about distance, which does not have a little accent, little hat on top, distance is literally just how far did you go? Well, I walked 3 and then I walked 5. Wow, that's still not right. Because this was measured that it wasn't just about 3, it was 3.0. We're not sure whether it's 3.01 or 2. Because this was rounded and this was rounded to 10th now it's the same thing. That doesn't necessarily work, right? One is the path you take. The other is start, finish. Everybody cool with that? Okay. So let's try some formulas then. You probably learned these in grade 10 at some point. One of the first things that people calculate is your velocity or your speed. And those really work the exact same way. Sometimes you care about direction, and sometimes you don't. If you were to ask me, this is a dumb example I gave the first class, but let's say you got pulled over by a police officer for speeding, and they asked you, do you know what your velocity was? Boy, don't do this. This is going to get you in trouble. But you can say, well, it was nothing, because my displacement for the day was nothing, because I started in bed and ended in bed. Do you get how that would kind of work there? Because velocity is all about based on displacement. Speed is based on distance. So you can make some really bad arguments, but ultimately this, I'm going to skip forward here, is your formula. Your velocity or speed is your displacement divided by time. If you want it to be velocity, you use displacement. If you want it to be speed, use distance. The distance that you traveled is different than the displacement that you traveled. So back to my really bad getting out of a speeding example, right? Like, technically, if you wanted to know my velocity for the day, it was nothing. And the reason why it was nothing is that my displacement was nothing. So therefore, if I had no ultimate displacement, then I had no velocity. But did I actually have a speed? Yeah, I had speed though, right? So anyways, it's a pretty basic formula. I don't want to overspend time on something that you're probably familiar with. Let's do a really basic example. A person walks 10 meters away from a stop sign in 5 seconds. What's the speed of the person? Okay. Speed, which is v, is distance over time, which is 10.0 divided by 5.00, which is 2. I can be more specific than that, because 2 kind of implies that, well, maybe it was actually 1.97 and we rounded up. I can tell you with more accuracy, no, it's actually 2.00. I don't know what comes after that. But like I have a decent amount of precision on this. You traveled 2.00 meters per second. That's pretty easy so far. You probably learned that formula in science test. Well, if you're not traveling the same speed, then you're accelerating. And acceleration is basically the next level up. And there's 3 ways you can accelerate. You can speed up, you can slow down, or I hop around. I suggest like take your phones out to follow along if you need. Uniform motion is basically when you're traveling in a constant rate of motion in a straight line. If I basically walk like this, I'm undergoing uniform motion. It's pretty boring, but I'm going the same speed. No, again, speed. I'm going in a straight line. That's very uniform. What does the word uniform mean? I think another synonym would be like same. If you're undergoing something that's always the same, it's uniform, right? Like when you have school uniforms, it's so that everybody is wearing the same thing. Well, uniform motion is usually when you're trying to do a distance over a time for velocity. Acceleration is different though. Acceleration is not going the same anymore, right? Something has to fundamentally be different. So you can either change the speed of the object, and it either speeds up or slows down. But another way to change that sameness is change the direction of traveling. If I was traveling this way, and all of a sudden I turn and go this way, I've actually accelerated. But the reason why I accelerated is because my direction. That's another weird way that you can accelerate. Even though I'm going as normal, I'm no longer uniform. Right? But really, there's only 2 options. You're either traveling in a uniform, same sort of manner, or you're changing. And you've probably all learned this formula at some point in grade 10 as well. It's straightforward. It's that the acceleration is equal to the change, and that's why this delta has to be here. The change in velocity over change in time. Chances are, like, the numerical amount of your speed and velocity has to have changed. Otherwise, if it didn't, you're not accelerating. That's why the delta is so important. Sometimes we get lazy and we just write A equals B over T, and that's probably fine. So just so you guys are aware up front, if I don't write a delta symbol, It's probably just because I'm being lazy. But in its fundamental core, there has to be a change in velocity. And I guess at the same amount, time has to change too. But that being said, doesn't time always change? When does time ever stay the same? So let's try an example. Let's say that there's a boat and it can accelerate at 4.5 meters per second squared. It undergoes a change in speed of 18.5 meters per second. How long will it take? This is the core of what I want to work on today is now that we've talked about how to measure numbers. Now granted, this is 4.5. That's where they decided to stop rounding. It could have been 4.5192. But they could not guarantee those numbers, so they stopped there. Fair enough? And someone measured a speed. It might have actually been 18.49712, but they couldn't guarantee all these numbers, so they just rounded it up to 18.5. Now, the next goal we have is, can we take formulas and just plug numbers in formulas? And it's a lot of algebra skills. So I would say that there's two main ways that students like to solve algebra questions. I'm going to sit at the back, though, if that's okay, because the back is going to be important here. Method number one. So we know the acceleration, right? It's 4.5. So acceleration becomes 4.5. Your change in velocity is 18.5. And time is what we don't know, so I'll just leave it as t if that's cool. And then you just got to algebra it. I like to use algebra, not a noun. Can you algebra this? So as long as you got good algebra skills, you just need to isolate for t. How do you isolate for t? Okay, no? Go for it. Perfect. I mean, what you just described is, you guys ever heard the phrase cross multiply and divide? That's basically what you did, is you multiplied both sides by t, and that cancels. T is now in the numerator. That's really important. You can't have t being on the bottom of the fraction anymore. And then for the last step, it's still being multiplied by 4.5, so if I divide both sides by 4.5, that cancels. And so, long story short, t is whatever 18.5 divided by 4.5 is. So, calculator. 18.5 divided by 4.5. You get 4.1 repeating, which then leads to why I had to teach you yesterday's lesson. Sometimes students, they get a little bored with the sig-dig stuff. Anybody lose marks in grade 10 for like sig-digs and like you are not happy about it? No, you're like, the stupid sig-dig stuff. I'm hoping that I'm explaining to you why it's so important. Now, it's not life or death in grade 9 or grade 10 or grade 11, obviously. But it is in certain realms. If you're an engineer, if you're working for NASA, we need to know where can we stop guaranteeing the accuracy of this number. We've calculated 4.1 repeating. The rules that we've taught you is because 4.5 has 2 digits, we're going to cut this off to 2 digits right here and say all that I can say with certainty is that it's going to take 4.1 seconds. Let me show you why, though, why this is so important again. This number 18.5, somebody measured it and decided to round to 18.5. What if they actually made it 18.5132? Wouldn't that number round to 18.5? And hypothetically, let's say that 4.5, when someone measured it, that they actually could have measured it as 4.51. No, let's go the other way. Yeah, let's go with 4.44959. Would you guys also agree that 4.495 would also round up to 4.5? That's very reasonable. So let's say that someone measured slightly differently. Well, now let's calculate what that tells us. 18.5132 divided by 4.4959. And I end up getting this number instead, 4.11779. Well, if I kept writing it as in the initial example, 4.11111, what was this one right here? Was that a certainty? I guess not, because in theory, maybe it could have been a 7 right here. Right? And let's say that I change these numbers even more. This number down here could have maybe been as low as 4.4, let's make that a 759. Wouldn't that still round up to 4.5? Let me try that. 18.5132 divided by 4.4759. Now it gave me 4.13619, etc. What two values aren't changing though? The 4 and the 1. That's what I can guarantee. Everything after that, there's too much of a margin of error. Is that a good word to use? And if it's not within my margin of error, I don't write it down because I don't want to accidentally say, oh, you can have a certain amount of time, and then I give you too much, and oh, you missed that window for something, right? I've got an example we're going to do in a bit here. I'm going to hop to it now just to explain the concept. We're going to do an example in a little while where someone has to pull a parachute cord. And the question that we're going to solve for is what speed do they need to travel when you open the parachute? That's pretty important. If you're traveling too fast or too slow when you're opening the parachute cord, that could have drastic consequences, right? And so it's very important to be exact. Anyways, we'll do that in an example in a bit. Okay, going back to this example right here, that's a very valid way of solving, but I'd like to suggest another option. Rather than taking your formula A equals delta V over delta T and plugging numbers in to solve, I actually advise doing your algebra first. Rearrange the formula first and then plug in numbers. And for day 2 of physics, I think I'm just going to have to tell you, trust me, I think it's a better option. The first option works, okay? But I'm going to show you over the course of the next semester and even the one after that, it's usually advisable to do your algebra and then your substitution. The steps are the same. You still multiply both sides by delta t. You still multiply this side by delta t. And that cancels. You still divide by a on both sides. You get the formula of delta t equals delta v over a. You still take 18.5. You still divide by 4.5. But do you see how the order changed just slightly? I promise you, I have good reasons for suggesting method 2. But I can't show you them yet because we're working our way up. But there will be scenarios where I think it's valuable. And that's really what I have on this slide right here. Is there's 2 ways you can do this. Either put numbers into your formula and then do the math, or algebra first, and then after you algebra, then plug numbers. Okay, now that probably I know there's some other ones on energy. We'll get to them eventually. I'll show you other formulas. If you know how to solve one formula, you kind of know how to solve all of them. Because it's really about rearrange the formula, and when you rearrange the formula, plug in numbers. So here, it's your... And at first, this is overwhelming kids, because they're like, holy crap, this is a lot. Couple of thoughts. Number one, we're going to learn these formulas slowly but surely. And number two, though, I really do say this, that if you understand how to algebra, you don't know how the formula Fe equals K Q1 Q2 over R squared works. You don't even know how it works. As long as you know how to divide, if you can do algebra, you can solve the physics part. You just need to know what the heck K stands for or Q stands for. Is that fair? So what we're now going to start working on is we're going to make some new formulas that always involve distance, speed, acceleration, and time. And we're going to put some formulas together and make the core 6. They're called the kinematics formulas. I'm kind of cheating. I'm putting them before we do energy. But these are your core formulas that involve distance, acceleration, and time and stuff like that. And some of them, they even make a lot of sense as to where they came from. For example, this first formula up here is the one that you've already learned. Your average velocity is your displacement over time. But what if you're not going the same speed the whole time? What happens if your speed is changing? Well, that's how this formula came to be. What if you have an initial velocity? That's what I stands for, hey? What if you have a final velocity? What if your velocity was, in theory, changing? Well, what if you add up your initial and final and divide by 2? You know what you just found is your midpoint. You found your average velocity, right? And so in a way, this right here is your average velocity. And if you then took this formula right here and just rearranged it and times time up over here, do you see how they're kind of the same as each other? And then you can do funky things like say, well, this formula here, d equals vf plus vi over 2 times by time. But what if I took this formula over here and I rearranged this formula so that time was equal to a change in velocity over acceleration. So rather than writing time right here, I write a change in velocity over acceleration. You see how I did that? I took this formula right here, I swapped these two around, and I made time be velocity over acceleration. And then right here is where time is. If I then plug this into that spot right here, I get this. Well, then change in velocity is really velocity final minus velocity initial. If you were to multiply 2 and a up to the other side, you now get 2ad. And if you were to FOIL all of this, you end up getting velocity final squared minus velocity initial squared. And now you're getting the beginnings of this formula here. Now, if I lost you as to how I did that, that's okay. You don't need to know where the formulas came from. I just need you to know that there's the formula. Is that okay? No, but like the formulas come basically from like doing cool algebra. Has some formulas. That's our main goal for the day. So new example. Accelerated at 4.5 meters per second squared. The train takes 20 seconds to slow down, and when it's done, it's the speed of 2 meters per second. The question is, how much stop? When I first teach kids how to do physics examples here, one of the things we'll do is figure out what formula. Like on that sheet, there's like we're not using all of them. Decelerating up. Wait, it also told me the time was 20 seconds. And it told me to slow down. That sounds like a velocity response. Moving up to solve. A lot of kids find it very useful to write like framework, write down the values of all of the fast and static. Then you're up to your algebra. Do you know how to plug numbers into a formula? I don't even have to do any algebra. I can plug numbers right in. If you have a calculator, try it, I guess. 2 times 20 plus, no, not plus, minus. Well, you could make it a plus. It's a double negative, okay? A half times negative 4.5 times by 20 squared. And if you do all of this, you get 940. Distance is in meters. And now we got to talk about rounding. I know your calculator spit out an answer of 940. Is that a valid way of representing our answer? Is this 940 right on the dot to the nearest meter? Well, when I look back at all the values we had, all of these had 2 digits of significance. So when you're thinking about this 940, 940 is a fine answer. just make sure that in your mind you realize that it's because it's rounded to the tens, right? This is because it landed on the nearest tens increment. It may be better, just for the sake of clarity, to write 9.4 times 10 to the 2 meters. That solves the ambiguity of whether it was rounded to the ones or the tens. You could even call it 9.4 E2 meters. That's valid too. Either of those works. How's that? Pretty straightforward? What was nice about that one is that you literally just plug numbers into a formula. Right? But what if the formula is not in the same order? Ooh, I lost my picture somehow. There was a picture of a parachuter here. Hang on a sec here. My smart notebook has lost all its diagrams. Give me a sec here. I'm going to reboot it real quick. Weird. We don't need the picture of the parachuter, but it's not the problem. Close that. Don't save the process. There's a parachuter flying 5-3 kilometers above the ground. He decelerates again at a rate of 3 meters slash second. For what it's worth, meters slash second is meters per second squared. If you haven't ever seen that before, this is just meters per second squared. It takes less than a second for his parachute to unravel. But in the time that his parachute unravels, he's still traveled 34 meters. My question for you then is, what was the man's velocity when he initially opened the parachute? So let's start the same process. Let's start to write out the variables we have. For example, I know that the distance he traveled was 34 meters. But then some kids say, hang on, what about this 1.53 kilometers? That was not really relevant information. We call it a distractor sometimes. It's distracting information. Because what we really care about is when the parachute unravels. I don't care that he was 1.5 kilometers above the ground. I care about the fact that he went 34 meters while his parachute was going pop, right? So that's our distance. We know that the time it took the parachute to pop open was like less than a second. We know that it decelerated him. It slowed him down at a rate of negative 6.3 meters per second squared. By the way, how fast would he have been speeding up due to gravity? Do you guys remember the gravitational amount? Yeah. And so this is preventing gravity from speeding him up by re-slowing him back down. Does that kind of make sense there? Right? He's not actually going backwards. The parachute doesn't actually keep you from falling. You still go down. You're just not traveling down nearly as fast. Right? So, and then finally, we've been asked to solve for the velocity initial. So if you kind of understand that as a framework, we're now looking for a formula that involves a d, a t, an a, and a vi. So I'll go back here. Let's try it again. We need a d, a t, an a, and a vi. What formula has all four? It's this one down here. What you might notice about this one, by the way, is it's almost a carbon copy of that one right there. The only difference, well, there's two. Can you guys see the differences? This is an I, and I'm sorry this kind of blurs together, but that's an F. And this one is a plus, and that one's a minus. That's it. Otherwise, they're the same formula. So, what I like about doing this one here then is, where are we going here? This slide here. Oh, goodness, Chris. There we go. Is that I'm basically using the exact same formula structure. D equals VIT plus 1/2 AT squared. And we are being asked to solve for VI, which means kind of like the equation 3 equals 4x minus 5. That's kind of what this is. D is like the 3. 4 and x are like the VI and t. And then over here, there's an extra term. So So just as a quick algebra recap, if you want to isolate for VI, it's similar to what you do here. Over here, you'd have to add 5 to both sides. And then once you do that, you divide both sides by 4. So it would be 8 over 4. That's going to make sense in a 30-second version. While doing the same thing here to isolate for VI, you're going to have to minus 1/2 AC squared for both sides. And that'll cancel that off. Which means you'll then have D minus 1/2 AC squared. And it'll then equal VI. And then just like you did up here in this math problem, well, then you still have the 4x. Well, we don't want t sitting next to VI, so we got to divide everything by t. So here's your formula. And this is one of the harder things for kids because it kind of requires me to take my classes. Algebra skills that you're comfortable with. So I do want to say this: if I lose thinking on the algebra stuff, but my goal right now is not specifically to reteach you all of algebra in an hour. It's just to point out how we're going to do it. As long as you're okay with that. Divided all of that again by 0.1. Oh, you're right. Square that. One thing I do want to point out is that these types of calculators, you're probably going to want to put a bracket around the calculator. If you understand how your calculator works, your calculator is a very literal device. It will take 34 and then minus all of this, and it will divide the 0.71 by only the second half of your statement if you don't put a bracket around the calculator. I've never shown that before. Make sure you're seeing it. 34 minus a half times by negative 6.3 times by 0.71 squared. Thank you. And then divided by 0.71. And if you do all of that right, you get this answer here. 50.123, etc. Now for the details. Imagine that you're skydiving. Tom Cruise in the most recent Mission Impossible movie, he is skydiving down from space to save the world. Tom Cruise does Mission Impossible. And in his helmet, he has like some sort of device that measures his speed. And when his speed reaches a certain velocity, he knows full altitude. Have you seen a movie like this where that happens? Right. Well, here's why this is really important here. Based on the data we've been given, this has 2 digits, this has 2 digits, this has 2 digits. When we are done, our final answer needs 2 digits, so 50 is a very reasonable answer, 50 meters per second. But can you see why 50 meters per second could be dangerous to some people? Does that mean pull your shoe or when it exactly fits? If Tom Cruise pulls the parachute at 51 meters per second, that might be too late. He needed to pull it when it exactly was. But when you read that number there, some people may interpret it as 51 is close enough. 52? So you may not want to write it as 50. You may want to write it as 5.0 times 10 to the 1. Just to be clear. It's silly, it's a little node. Right? But so that's the whole physics kind of chemistry, right? Is that we don't want to do things when you're building or when you're sending fruit down. Or when you're sending a Mars rover to space. What ended up happening was one of the machines that was 7 was one new and even if they do, some of them require 3, but you need a combination that just so, but like before you shot the bullet, well, who's the bullet? Because it wasn't moving. Now I know the question is, but there are some times in physics where you gotta read between the lines and recognize, well, okay, this wasn't possible. We have a lot of examples of these problem objects and the initial velocity. Oh, gravity. One more thing I want to point out is the 75 centimeters is the right thing. We normally like to work in meters. So you should really make this 0.75. Divide by 100. That's the right thing. Speeding up a little bit, we want to then go back here and find a formula that involves Vf, Vi, speed, race. Well, that formula here involves Vf, Vi, speed, Vf, Vi. So the formula, if you have it on your formula sheet, was Vf squared equals Vi squared plus 2AD. And we got to isolate for Vf. Well, Vf is almost isolated. Squared. How do you get rid of a squared factor? Okay, now a quick thought here. This is not what you do. Do not do this. Do not square root each term. That's not how square rooting works. When you square root the entire side. So if this was Vf squared, you square root the entirety of one side or the other. So you actually square root all of it. So your final formula will be Vf equals the square root of Vi squared plus 2AD. And then the sign goes all the way up. What kind of at a certain point, is there a likelihood like that you're rearranging math a little bit differently? And that's why I also say if you know how to do 5 examples, do 3 examples. Right? Like if after 3 examples you're like, yeah, okay, okay. Velocity initial is 0, by the way. What was the acceleration? 5, 5. The distance was 0.75. Don't forget, we had to make that in Dutch. 2 times 535 0.75. Square root the whole shebang. You end up with this number, 895.8236. And back to safety. Okay, what am I confident in? Digits do I have confidence in? I think it's 75 centimeters. I only have 2 digits of confidence. So I've chosen this one purposefully as well. I'm confident that we're in the 800s. I'm confident that we're in the 90s. And then after that, I'm really not confident. I'm not certain it's 5. That being said, 5 is enough to be halfway. So since 5 is more than halfway, I'm actually going to round this to 900 meters per second. But I'm implying it's rounded to the tenths. Does that make sense there? Maybe a better way of writing is 9.0 E2 meters per second. I am confident of the 9. I think it rounds up to the 10, but that's about all I can say with certainty. And because 5 was more than halfway, I chose to round up. I was a precision. Again, you're Tom Cruise flying on Williams Mission Impossible example here. Here we have a little bit more generousness to it. I'm not 100% sure what we can get away with. Somewhere in the 890 to 900 range there, but I don't know exactly. Right? So in there is the right value, but I can't pinpoint it any more than that. Okay, we're almost done, I promise. We have 10 minutes left here. I'll be wrapping up here. Here's kind of a slide then. This is what I wanted the picture showing up. But anyway, slide that might help you then identify which formulas to use. Of the main variables we have, there's a formula for basically everything with the exception of one, right? So if you don't know time, time is what you're not aware of, then you use this one. If you know nothing about your velocity initial, you use this one. Half the battle is figure out what formula to use. The second half of the battle is can you algebra? Please use my laptop. There is a scenario which the quadratic formula is used. And sorry for those of you who haven't used the quadratic formula before, I'll show you this. But the quadratic formula is for a scenario in math where I don't give you 3x plus 4 equals 7. Because that's pretty easy to solve, right? You minus 4 for both sides, you divide both sides by 2. It's also not for the scenario where x squared equals 9. Because in that scenario, you can just square root both sides and you're good to go. It's for the scenario where x squared plus 5x plus 4 equals 0. And then I ask you solve for x. And I go, I can't. Because there's an x here, and there's an x here. See the problem? And they're not like terms, so you can't really combine them at all. There is one scenario using one of these formulas where when you're solving for a certain variable, it's impossible to solve for that letter by itself. This one right here versus this right here, when you're solving for it. Hypothetically, let's say I give you the formula d equals bit plus 1/2 at squared, and I say solve for time. Using traditional algebra methods, you have a t here, and you have a t squared over here. You've learned the quadratic formula. It's a nice shortcut to help you solve. I'm going to show you one quick example on this. I'm not going to make you do this particularly, because that's not the point. The point is for you to see the overlap as to how what you've learned in math can be applied to physics. So here's my last scenario. This is an F-22 traveling at 97 meters per second. So I know a velocity. It hits the afterburner and accelerates at a rate of 26 meters per second. It was traveling 97 and accelerated. I think that was the velocity. It doesn't say as much, but that's implied. It tells me that we're going to travel for 3.2 kilometers, and in my head I'm just going to make it 3,200 meters just to save us some time. And the question was, well, how long will you need? So imagine that, those are sad things to imagine, but imagine that it's wartime, we need to send out a plane, it needs to travel 3.2 kilometers to go bomb a target, and we want to know how long it needs to do it. Right? We know the speed it got off at, we know how fast it's accelerating. It's going to be hitting Mach 1 pretty quick here, but the question is like, how long do we have to wait until air support is there? Okay? So we got to solve for time. Well, when you figure out which formula to use, it's this formula here, d equals bit plus 1/2 at squared, but you can't solve for time. Well, not with the traditional method. So here's how you would use it. Well, we do know traditional method. We do know velocity initial is 97. And rather than calling it t, let's call it x. And quadratic formula and solve it for you? I'm not asking you to do that. I mean, not regularly, and if you do, I'll help you with that step. So that's kind of a tricky one. Solving for time in one scenario is that, especially if you have to multiply that. Great question. Okay. For those of you who've taken Math 20 class, some of you might recognize the term extraneous solution. Do you recognize it? Sometimes there are answers that are non-logical. Let's say that when you're done, you get two answers, and the time value is -5 and 12. Well, you can't have negative time. It's not logical. There are some scenarios there where maybe both answers are true. Now, this particular scenario is not really possible to solve for the amount of time that and have two answers. This is a different scenario. I think it's on my screen. Imagine that you had a catapult trying to shoot a rock at a castle. They're really fast. And let's say that you were allowed to shoot a rock at a castle, and it went up on a trajectory on the way up, and the rock hit the castle on the way up. Or you took the catapult further back, and it went up in the air, and then catapult the castle on the way back. Do you see how it's actually logical that you could solve for time? Because it would take less time to shoot the castle on the way up. It would take more time, but on the way back down, it's also fast. So it is actually possible for you to have two answers, or one of them extraneous. I don't actually want to solve this particular question. That's not really the point. But my final point of understanding is I want you to understand, for those of you who are doing math simultaneously, is that there is an overlap for algebra. There are other ways to solve it. Okay, let's recap my three main goals. And if you'd like to, you can maybe take the last 5 minutes of class, because we only have like 5 minutes left. But you could start writing about some of these things we talked about. I don't care what you write. Don't do this for me. Also, don't do it just to get a check mark. Like, don't write one little bitty sentence just to get it over with. Okay? Do it for you. Do it to solidify the knowledge of what we talked about in your mind. And maybe actually don't even do it right now. I will give you 5-10 minutes in your class tomorrow to work on this. And it's just a good way to think about what we just did. Right? So, do you feel like you know the difference between vector and scalar? Do you feel like you know how to algebraically rearrange formulas to isolate? How are your algebra skills? And in that one possible example, do you know how to use the quadratic formula? And it's cool if you don't, by the way. I'll show you. We'll work on it. You will learn it in your math class at some point. And that's it. Okay. The other thing to work on, by the way, is at the end of this lesson here, I'm going to put a YouTube video in here. So eventually there'll be a YouTube video of this lesson in here. You can do some practice questions. So let's do one together, and you get picking up anyways. A book is dropped from the top of a tower from a height of 350. The book takes 8:45 seconds to fall. What was the average velocity? Don't overthink this one. This is literally our first formula. What's the average velocity? Distance divided by time. Take 350, divide by 8:45. Ta-da! Make sense? So, anyways, try these 5 questions. Plan tomorrow, then we'll go over these 5 questions. We'll talk about and we'll look at some of the reflections you wrote. If you have questions, we'll go over them. And then tomorrow we're going to do a lesson on graphing. Sound good? Cool. Okay. Feel free to pack up and take off as you need. I guess we're kind of done. So.